Mircea. Mircea. Yeah, like nice to meet you. Mircea.
Okay, yeah, let's get started with the second part of the day. So, Mircea will present us something about the mathematical connections of local to global expressivity results.
Okay, so thank you very much for the introduction. I will. The plan of the talk is I will talk about result which you take message passing based on distances between points in Euclidean space. So I call it geometric message passing, following some of the terminology. And I give you a little bit the idea of the proofs. And then, since this will be short, and then after mentioning the results, some results that about that, I will basically go on with some open questions and directions. They are with a mathematical point of view, like the title was saying. So I didn't cheat, on you. But I will try to make it realist, in a sense, to kind of connect to reality, in a sense. Yeah, connect it to more realistic applications. So the first part, right? So here I try to see the picture, the description of the problem from a little bit far away, right? So I have some graphs, and then we care about edge and node labels. And then what we care about, so for example, here the main example is this. You take aggregation and some neural network on neighborhoods, and then you do it for, you repeat the processing for k steps. But this, I mean, one could think of it like what you really have is the traces of what happens when you apply a class of functions that act locally and are applied at each vertex, on the neighborhood of each vertex. And in theory, if you take the whole traces or whatever it does at all the processing by these functions, would be kind of equivalent to just take the image of that of those functions applied to each graph. Yeah, and then what we do is at the last step you take all the node decoration that you got and make a set, multiset out of it. I should have put the multiset notation, multiset for each graph, right? And then the question here we address is about how much information is lost about these graphs from this class. So does this multiset here again should have double brackets to remind that it's a multiset. So if I have this multiset, will it allow me to recover G, right? So you see, this is like a little bit more than expressivity, because does it allow to recover, right? And in a sense, the proof allows gives you an algorithm, inefficient, but an algorithm that could, in theory, recover it, right? So it's kind of, the kind of results would be constructive, and I don't know, so I restrict to that kind of question, right? So as I say, now I would give an idea of the proof, and so I'm immediately restricting the setup, right? So I don't care about graphs that other graphs than the complete graph over n vertices. And the n vertices are connected with n points in Euclidean space, right? So labels of the points. And then for each pair of labels, I have edge decoration given by the distance of those points. And the simplest case, you start with node decoration, which is constant, or you put 0 on all the nodes. And then you do node color updates. And you are allowed to take the color from the previous step at the same vertex, or the edge and node colors pairs for the neighbors, unordered edge and color multiset. Yeah, and you do that for k rounds, and that gives you a class of functions that you can apply. And you can ask if the thing you process in that way is conserving the information about the graph. Right? So this is what I call geometric WL, right? Geometric in the sense that you start with edge decoration given by point distances, and the points are in a fixed space. But we don't say, we don't, and also like every point sees every other point, complete graph, right? And then the result is that the result is that in 2D, if you have points in 2D, 3 runs of this geometric 1WL can distinguish any point clouds. But if you are in 3D, you will always find counterexamples that cannot, where the method when you collect the node decoration at the end, this doesn't inform you which of the 2 graphs from the problematic pair you started with. So that's the example, one example. Here I have a regular hexagon, and you can read out what are the edge distances that I have. And now I take 2 triangles that are sitting a little bit one above the other in 3D. So I look at it from above, but 2 equilateral triangles, yeah? And there is some magic that happens that if I put it correctly, then I recover exactly the same numerology of the distances, and in fact every neighbor has, if I color the edges like that, has the same multi-set of colors around it in the 2 graphs. So in a sense, if I start and I propagate the information with no node labeling, and then I start repeating the process, I can do it as many times as I want, but it will not change. It will not distinguish the 2 graphs because it started with the same information at the first step. Yeah.
Good question. So what exactly do you mean by reconstructing the graph, right? Because if you take distances, that's not necessarily unique.
Sorry?
Right? You can have the same. You can have 2 graphs with.
Which have? Wait, maybe I'm missing. I say something that I miss some part of it.
So if you have pairwise distances, right?
Mm-hmm.
Two different graphs can have the same pairwise distances.
Exactly.
So what do you mean by reconstructing? If you have,
but then every
node
node here sees the label of the others, which is constant, and the set of distances together with that constant, and then it propagates this information, can manipulate it, and then it can only use that information no matter how, right?
So you want to reconstruct the distances.
And then what I want to, this is a good point. What I want what I want the method to be is injective over congruence classes of the graph, or like congruence plus symmetry classes of the graph, right? So that if the 2 graphs are the same shape, they should they are automatically identified. But if I would like the vice versa, that if they are different shapes, they would not be identified, right? So if this map from the shape of the graph to the shape of the point cloud to the final information that is this collection of final labels that I processed, if this is injective, then there exists a reconstruction map. Do you agree? And then the reconstruction is up to shape, up to isometry.
Right? We understand like what do you mean by reconstructing the graph?
So it means that I could, in theory, recover an example of the graph up to isometry.
A canonical representation of this class, right?
Of this class. Thank you. Does that make sense?
Up to permutations and rigid motions, right?
Yes.
Can we
Yes.
construct something up to permutations?
Yeah. So I just care about the point cloud up to isometry. Yeah.
Okay.
Mircea,
Yes.
do we know, perhaps, yeah. So if I give you a graph with colors on the edges, is there a representation of this with distances? I mean, like, because if I give
There
you
is so we assume that there are numbers. The colors are actually
No, I
numbers.
know, but if I just give you the colors, and I want to know whether this can be realized as a 3D.
So what I know is that there is
in 2D, right? For instance.
Like I don't know the answer to that. I know a hint to that, which is if it was numbers, then what you would do is there is a criterion about you construct some metrics based on these numbers that are kind of reconstructing the gram matrix information. So some differences to the number squared, and then if that matrix has a given rank, like something like the dimension, then they are embedded. Then this set of distances comes from a point configuration in that dimension. Otherwise, not. Then the question is, you have I only know if they are equal or they are different, and I don't know the answer of this information mapping to actual true numbers that give you this rank. Yeah, but in theory, yeah. So I don't know the answer.
Okay. Okay. I think. Sorry, you can also think of it iteratively, right? So assuming that you already put down n-1 point, and there's a rigid graph, so there's only one way of doing it, and then you add one more point. And if you're in the plane, then unless two things line up or three things line up on a given line, then two distances define where you need to put the new point.
Yeah.
And the next. Okay, so
that's the proof. This is the proof I'm going to talk about. Thank you. So it's a very simple proof in a sense, but but before the proof in the case, I just to mention that you have a generalization of this because. This is a negative result. So there is a generalization that says you start with a different object, not exactly as in the beginning. Your points are replaced by L tuples, ordered L tuples from your set, and the decorations are, or like the coloring at the beginning, are L times L distance matrices. So. Something bigger, yeah. If you have L equals to 2, that would be pairs of points together with their distance, yeah. And the coloring is their distance. And then the new color, it can depend on the previous color at the previous step. And then you do this other operation that you take the color of the previous step of tuples, in which you take the initial tuple and you replace a vertex at all possible positions in the tuple. See, this it means I replace this y to the position L. In the tuple, here I replace it to the position 1, and so this is an L tuple of colors from the previous step, right? And so, for example, if I am in 2D, then if this is y, then one of the elements of this multiset will be kind of equivalent to the edges of this triangle. Right, and if I have this L equal to 3, then you work with triples of points, and the information associated to one choice of y would be the triples in which you exchange one of the vertices by y. So my main message to remember about this is that this has to do with triangulation of points, right? So you're kind of have enough information to start triangulating one of the point with two base points. Right? But here, the difficulty is that you are working with a multiset in which it forgets the ordering. Right? You have to forget the ordering, like we heard in the talk by Professor Condor, because this is how this message passing respects isomorphism of the graph, right? Automorphism of the graph. Okay. So the proof here for the case of 2D is that after the round 2 of this processing, there is something about the Euclidean distance in the plane, right? So our strategy is like this. You have access to the barycenter distance from the point, because if you take a set of distances from all the other points that you are allowed in the first step of this message passing, then the sum of square distances is kind of equivalent to the distance to the barycenter. Yeah, due to the properties of the inner product in R2, you kind of reorder the square, right? So I'm hand waving here, right? But the main thing is that you have access after 2 rounds. You have the access to the distance between a point and any other point together with the distance of that other point to the barycenter. In the second round of this iteration, yeah. And this is the main hand wavy part, right? And then we consider this distance statistics there that is available. And this distance statistics is, again, distance from a fixed point to any point and the distance to that point from the barycenter. And then we have this cone condition that is important. We will always have enough data in order to find 2 points that form the smallest angle to the barycenter, right? And that gives you the certificate that in that cone there is no other point from the set. Yeah, so if it has the smallest angle, there is no other point inside this cone, right? There could be points on these 2 edges, and you have to treat that case separately. And I don't treat that case here in this idea of proof. But so you have this you can, in theory, select candidates for this cone condition. And then we will work with this, with the data of the distance between those two, such a pair of points, and these distance statistics from the 2 points. These are available. If you have available that thing at round 2, then you have this available in one more round. Yeah? So at round 3, you don't need to do all the processing. You just need to have access to this much information, right? And then the algorithm. So the algorithm, let's say that B is 0, because we can. Our goal is to recover the point cloud, and that we are sure that our information encodes a given point cloud up to translation, rotation, and reflection, right? So up to translation, we assume that B is equal to 0, so we have that information. And our point, one of the points will be on the circle around the origin of a given length. So we have that information. And then we can fix V, like we have the information of distance from U to V, and the distance from the distance from V to the barycenter. And then we kind of fix V either on this side or on that side. There is a unique relative position of UV and the barycenter up to isometry. Yeah. And then for any other point that is not U or V, we have access to. We can determine Y up to reflection around this, but from the information of U minus Y and Y. And we can determine the point up to reflection with respect to the other line, the line from the barycenter to V, from that other information, right? So every point can have up to 2 options of their positions. And the question is, when can I exclude that it has 2 options? Where there are some cases in which the point, if the point is not too far from this line, so if I say that my cone here, I have here the barycenter, here I have the point U and the point V. If I have a point in this region, then that point, these 2 options for the point given by criterion 1 of them cannot be true because I say that there is no point inside this cone. Yeah? So that will happen that there will be some points in my set that have a uniquely determined position. And I can do that same thing on the other part. If I have some point which is too close to V or too close to U, then these points have uniquely determined position. Yeah? And so I put that points in the only option that they have, and then I go on. Now I have fewer points that that might have 2 possible positions, right? So if I had a point here, in theory the position can be here or there, reflected with respect to U. Yeah? But the region of where I completely determine my point set increased, right? And that's the principle. It will increase for a while until it's finished, right? It depends on the point cloud, because if this angle is very small, you have many steps, and then you have to try to these points Y you have to try many times, to try all of the possible candidates that come from your message passing, to put them somewhere till you exhaust all the possibilities. So in a sense, it's kind of expensive to do that if you want to recover it in practice. There was a question, I guess. Yeah.
So you say that the new points, say y, is sufficiently close.
If it's closed, then
And then you can uniquely determine.
I can determine either it's here or is symmetric to here, to that line, for example, right? From the information of u minus y and norm of y, I can determine that either it's here or there. But here it cannot be because these points are chosen like with the minimality property. So it must be here, and I erase it from my list of points that I don't know where they are.
It's too far away. Then
If it's too far away, I don't know. I keep it in the list of unknown points. Right. Right. So this is the basic idea is that you have access to triangulation information, and then you continue it, right? If you are in 3D, it's more complicated, but you have still access to similar triangulation information in one dimension more, and the cone is going to increase at every step, yeah? And then, okay, there are some technical details to be sure that these cones don't leave any gap inside the whole cone angle and so on, but I feel that the idea is believable that if you stay with me till now.
Sorry, I'm completely
Yeah.
blank on this right now, my fault. So how do you determine
Me too.
how messages are being passed? So, because you have
Sorry?
a point cloud, right? And you said you're using message passing. So along what?
So in this case, I am simplifying my life because the initial label is constant for everybody, and effectively I only pass the distance information, the edge color information.
Yeah, but so between all pair. So that's what I'm not understanding. I think is it that you do message passing between any pair of nodes? Or
I do message passing, yeah, at every step, all my points get the information of some multiset of distances from all their neighbors.
Yeah, but how do you, so this is what I'm
Yeah.
thinking on. What is the definition of your neighborhood? Like how do you,
The neighborhood is all the other points because I'm looking at the complete graph.
okay.
Yeah, complete graph. That's a problem. I mean, if you have too many points, it's a lot. Right? Okay, so
So perhaps because what you said is that we can reconstruct the graph.
Yeah, so-
Another way to say it is that if you have two of these complete graphs with distances, and they are indistinguishable over two in 2D, right? And they're indistinguishable by 1 WL for 3 rounds, then they're isometric, right? That's, yeah. And the way we prove that is by showing that we can reconstruct the, yes.
Okay.
Mhm.
But this is only true if you have a fully connected graph.
You
yeah, a
have a
complete
fully
graph.
connect. I mean,
Because
yeah, I don't know.
typically
We
you don't
haven't
do that,
really
right?
thought about it.
This
but-
is one of the open questions.
Yeah, okay.
Okay.
Yeah, that for me open. I mean,
Yeah, so so what happens if you're outside of that arc? Because you're saying-
if I am outside,
Yeah,
what happens is that I know that now my cone of knowledge increased. And the number of points that I mean, the cone of cone where all the positions are determined is now larger. And so I repeat, and now I say this one, well, it could have been either on that side, if I look at the first criterion with respect to you, it can either be here or somewhere there, but now there it cannot be because I excluded that in the previous step. So this point is, if I would have, if I continue the reasoning, then now this point, it cannot have been here because it would have been selected according to the criterion with respect to V, right?
so you're choosing the points in order? Like,
Yes, I can at every step I check how many points are determined with respect to the in the criterion in terms of U and in terms of V, both of them, both of the cases, right? And this one was not determined before, but now if it would have been determined in terms of the criterion with respect to V if it had been in this position. So I would have cancelled it from my bad point list at the previous time. Yes, sorry.
Can this lead to some hardness result of computing formal house of distance for point sets in the Euclidean space, or in 2D in this case?
Sorry?
Can this lead to some hardness of like computing formal house of distance between two
So
point sets?
the algorithm I present is not intended for optimality. So in that sense, I don't know the answer to if this is the optimal algorithm for reconstruction. But it is intended in order to show that it is possible to recover the point set, right? I would not bet that is optimal. I bet it's not. Right?
You can solve the separation in n log n.
Yeah. Okay. I see. So no. So this is not. I didn't consider that question. Okay. So now. Here are some open directional links, and I hope you don't feel like you're losing time by listening to this. Yeah, but I would understand if you think so, that you did. Okay, so my full expressivity. The points are full expressivity up to a lower dimensional bed set, and then other topics. That is the last slide, and this is really last but not least slide, which is the only. Maybe the most interesting questions that I'm thinking about. Okay, so full expressivity direction. This is a full expressivity result in the sense that I have full recovery independent on what set I start with, right? There is no exception if I do this. And then the idea for me is triangulation idea. Yeah, you have you use triangulation strongly. Yeah. The challenge on that. Of extending this idea comes from finding correct other graph classes. We started here with a full graph, fully connected graph, and there is a good hope that you can do the same in other geometries if you are interested, right? There is a part here, like I said, when you get this barycenter information where you use the inner product, but one could argue that if you have a metric that is you have a quadratic form that is non-degenerate, not necessarily positive definite, then you still could get the similar result, right? So that, but I don't have a result. I don't. If you know it, please publish it, right? And I don't claim that this is written in the literature. And then my links, the links that I can see based on my previous past, are from rigidity and crystallization theory proofs. The toolbox from crystallization theory people, right? So the first part, the part about what is the challenge, right? So here we have, we use the complete graph G, but in many cases, we wouldn't like to have a list of distances that include all possible points in my point cloud, because, for example, in computational chemistry, you always fix a radius, and you just often you create a graph based on the point positions around that radius, right? So, I mean, in a sense, it would be useful for the computer chemistry realistic applications. Would be useful to have a local rigidity theory that would give you local reconstructions that you have a good idea when do they give a global reconstruction, right? So, in the sense, you are looking for classes of graphs in which the graph is not a complete graph, and then you can still certify recovery, right? Reconstructibility. For example, I can think of looking at nearest neighbors in a starting graph, or you have distance information only up to k neighbors, or up to distance up to a threshold, and if a distance is larger than r, then that's missing from your distance information, right? So that's how how would an incomplete graph look like? That would seem useful for more realistic connection with some of the problems. Yeah. Yeah.
So one point I wanted to make with respect to computational chemistry
Yeah.
applications. Right? So there, I wonder how much this matches what they need to do there, right? Because there, it's not just you care about up to isometry. You want different angles, so same distances, but different angles can have very different outcomes, right?
Mm-hmm.
So I wonder if this ability to reconstruct distances is actually kind of enough.
I mean,
in
it
that
would be
particular
just
application.
like the goal here would be that you find a certificate that the given processing of the information would work for recovering distances without having to look at all the neighbors, right? That's it.
I understand.
Yeah,
So
but I
understand
mean,
the theoretical problem. It's just a comment about the, since you mentioned also the radius of computation chemistry.
Yeah.
The angle does matter a lot, for instance.
Right, but I mean, so one of these higher order geometric methods that I mentioned at the beginning includes triangles of higher dimension. When you have a higher dimensional triangle, like something like that, then this has the information about the angle, right? If I look at the L times L matrix with L equal to 3, then, or even, yeah, L equal to 3, then it gives me the, actually this, even L equal to 2 has enough information to reconstruct the angles of this triangle, right? Which is not the proof I showed you. I showed you a proof for L equal to 1, right? So in theory, the angle information could be one of the, the targets for this, yeah? Of course, if you don't have angle information, you might be lost.
This would be a different problem.
No, it would be fit in the same class because we would like to do it to get the certificate when the graph is not a complete graph. Okay, and so what do we know? People have studied convex polyhedra, convexity. Convexity gives you rigidity for sure in many cases, right? So these are the results, mathematical results that are useful. It's just so my main message from this is that you have convexity of surfaces or like even higher polytopes in higher dimension. This is enough to give you that local information. So let's read this result. Two convex polyhedra with equal faces glued in the same way are equivalent in 3D, right? It's kind of similar to the spirit of our result. And this notion of convexity implying that you have from local to global rigidity is a strong notion, right? So this is easy to, is accessible for if you want to prove results. Yeah, that's the main, the main issue. So for example, there are also results for manifolds, right? That you have manifolds, surfaces in R3 that are analytic if the local tangent space inner products are locally mappable to each other by a Riemannian isometry, then the two objects are globally equivalent, right? And there are results that have these fractal embeddings and flexible embeddings of surfaces on the other side that show that if you don't have conditions such as high regularity and you have manifolds and you don't assume regularity and you don't assume how is it called, convexity or something like that. Convexity implies some kind of regularity, yeah? So if you don't have a regularity, then you have a lot of flexibility and you can do this Nash embedding where you take a torus, a flat torus, a torus that is not curved, and you can embed it so that it really, an ant walking on it would not distinguish it from a torus that is only existing in 4D, right? So in a sense, the local information is really, you can have a lack of local to global rigidity for if you don't assume some kind of strong control on your object, right? And the interesting thing is that that can go beyond the thing that you can draw easily into. They have results on these fluids that suddenly you see a bunch of fluid that is completely still, and at a certain point it will start moving, and then it stop moving, right? So they can construct objects like that is kind of pathological if you don't assume that they are very regular, right? So you have the lack of unique continuation in many cases. Okay. So well, what does it say? It can help in two ways, right? One way is that. Yeah, let's always start to think, starting from convex setting. So you use convex polyhedra and convex toy examples at the start. The other direction could be, can we use some version of geometric deep learning or graph learning in order to construct more pathological solutions? I don't know. I'm just saying some results, and maybe you are inspired to look at them. The other thing, complete switch. Now rigidity for tensegrities. So there is this, if you don't know what it is. Sorry? Exactly, I'm going to say.
Okay.
So a tensegrity is you have a bunch of cables, so things that you cannot extend. You have other things that you cannot compress, struts, I don't know exactly what that means, that you cannot compress, and then you have stuff that you can neither extend nor compress, right? So you don't fix distances, you have on some pairs of on some edges you fix equality to the given value of the distance, and the other edges you fix a lower bound and another an upper bound. And you don't use all the edges from your complete graph, right? So in a sense, the tensegrity is given by a graph over a bunch of vertices. You imagine these vertices embedded in Euclidean space, and require that some of the distances are fixed, some others have a bound from above or from below, right? And then the question on there, so this comes from constructions, right? From trying to find constructions that are stable, that will not fall down. And so in that case, there is the notion of rigid, which is the rigidity often means that you kind of find it's not rigid when it's flexible, right? This is not the same as in the other case, right? So rigidity means that either it can bend, starts from a position and then you can bend it, or if you don't, then it's if that position is kind of stuck, then it's rigid, right? And so this would be in some of the wordings say that this is rigid, right? Even if you could this part that forms a pyramid towards above, you can just flip it below, but you cannot flip it continuously, so they call it still rigid, right? It doesn't have a unique embedding, but it has a locally unique embedding, right? Pathological examples for that cases can be rigid, but at least they are isolated points. They don't form a one-parameter family of pathological examples. Yeah? So that's a bit the notion of rigidity. And then they have a notion of infinitesimal rigidity that implies a rigidity for tensegrities in RD. Right? So this is a nice result that shows that either you can test so infinitesimal rigidity is something testing whether at every joint I can move the joint I can find a derivative of the joints that preserves the constraint or not, right? So if you are used to convex duality, convex analysis and linear programming, probably this is you will find this trivial if you look at the details. Now I don't say the details. Yeah. Infinitesimal rigidity implies rigidity. And then there is this, I want to get to a result that Maxwell found a long time ago when he was thinking about electric electrons or charges. So basically, he was doing a simple computation. You have a bunch of points in RD, n points in RD. And then just for the sake of beauty, I am going to think of it as a function. I take a function for which I only interested in the matrix of derivatives, right? The function is all the square distances between points that form an edge of my graph. And then if I do this, I do the differential multiplied by another object of the same dimension, another point another configuration of n points ordered, yeah? Then I apply that, and then it gives me this. This is like the polarization of this quadratic form, right? You can believe it. If you start with this, then I get an element where it has this this property, that dfx times y is equal to, basically, I take the scalar product of difference of points times the difference of the other kind of points, right? And the idea is that I can think of y, n, the n coordinate of y, as a possible tangent direction in which my point is moving, right? And the fact that this scalar product, one of these scalar product for the edge ij is 0, means that actually if I move yi in the direction, I move xi in the direction yi and xj in the direction yj, then the length of this segment is not changing infinitesimally, right? So the kernel of this matrix gives me so whenever I find a direction, a set of directions y that allow me that these inner products are always 0, this means that the lengths are not changing, but I can still move the points, right? So the kernel gives infinitesimal flexes. Yeah, and then condition one can check in terms of the rank of that function how many infinitesimal flexes that don't come from actual rigid rotation of the set you get. So this is the dimension of the group of rigid rotations, and so the framework is infinitesimally rigid if the rank is equal to this value, right? That's a little bit something that Maxwell found this kind of simple reasoning, and in a sense, this can give you a criterion that can be useful in practice to work with rigidity in this challenge here, right? You can take local frameworks and then check the degrees of freedom using a simple algorithm, in a sense. Well, I don't know if more or less that seems reasonable. Right? So then here, from crystallization theory, there are two kinds of people that work on crystallization. One is predictable, mathematical physics, and the other is maybe less in dynamical systems, because in dynamical systems they have another interpretation of tilings, of how tilings form quasi-crystals and what are the periodicity. The periodicity of a tiling is like a dynamical system on it. So they have results that, I mean, they give ideas of what could be true and what could not be true when I try to prove rigidity results, right? So if you want to follow this line of work, you can take inspiration from some of these and try to you know, there is a creative side to this to see how you can use some of them, right? So this one guy, one nice Russian professor that has a lot of work on this rigidity. And all the results are for sets that are the lone sets. The lone sets means that they don't leave a big gap. So there is two parameters. One is saying that there is no gap of radius larger than small r. No. That no points are closer than small r, and there is no gap, no ball of radius larger than big R that doesn't have a point. So they cover everything more or less uniformly, right? So they work under that strong condition, which I don't know if is reasonable, but maybe in some cases can be reasonable. And then there is results on being a kind of regular, so being periodic, being the orbit of a group of isometries, so being kind of a crystal, regular, periodic. There is some condition on the number of clusters of a given radius up to isometry, and the isometry group of these clusters being constant if I compare a small cluster to a large cluster. This is the number of isometry, the cardinality of the subgroup of isometries of these clusters, and this is the number of clusters. And so if they have criteria based on those quantities for rigidity. And the other kind of surprising thing is that you look at the clusters and you check if the center of the cluster is at one point of the set, and then you locally antipodal means that you can switch x to minus x with respect to that center, right? So they have a criterion of equality of the cluster using only antipodality. So they propagate this property of being antipodal at higher and higher scales, and and they check equality of this kind of regular sets, the Lone sets, based on that property, right? The Lone was Russian, so he has everybody writes his name differently, even the same person, the same authors. Okay, and then there are these other results where you have another kind of rigidity, more suspicious, kind of strange. The rigidity says there exists a separated net, another name for the Lone set, the same notion. There exists the Lone set in the Euclidean plane, which is not Lipschitz equivalent to the integer lattice. So it says, in other words, if I take a lattice, I do Lipschitz equivalence, then it's the class of this up to Lipschitz equivalence is rigid enough that some of the sets that have that are well spread without holes are still in a different class. Yeah, you cannot connect two things together under. So there are notions of regularity of these sets, like being a lattice or being Lipschitz to a lattice, that are kind of counterintuitive. Counterintuitive what they give. And the last one, let's skip the last one. Okay, so the next part, expressivity up to pathological examples. Here, the group of Nadam Dim has a lot of results of different kinds of this, right? So the idea of this is that you find some pathological examples, like this hexagon in these two triangles cannot be distinguished, but there are really few of them. They are isolated in a sense, or like they are measure zero, right? They form a subset that you cannot separate the two by your algorithm, but they are. It's very rare to get those configurations. And the challenge here, which is a strong challenge, is to evaluate the practical influence of this pathological set, right? So there is this result of Butin Kemper, right? They were studying a very simple statistic of a point set. Just take all the distances between pair of points and make a histogram, the distance histogram, right? So they prove that the distance, so if I take the bunch of points and then I do the distance histogram of them, the pairs of configuration of points that have the same histogram form a lower dimensional subset in the space of all pairs, for example. That's a way to say it, right? So it's if you throw points at random, almost surely the histogram completely determines these points. But even stronger is the ones that are not completely determined are sitting in a big in a surface, in a subvariety of the space of configurations, right? So is basically it would say if I work with distance histograms, it's enough. Don't need to do Weisspeiler-Lehmann. You just take the statistic of all distances, is enough. But you have pathological examples, yeah? So, and there are many very nice results that work with spectra, diffraction patterns, histograms of the distances around the point, or of areas, triangles around the point, and so on. So it's a large universe, right, of possible fingerprints. So functions that distinguish point clouds, or say less restrict to point clouds, but they distinguish it up to pathological examples, right? And it's very fascinating. And for example, there is all this. There are results on the spectrum. Can you hear the shape of a drum, they said, but then other people were talking about point configurations like lattices. And then there is results which say that if you take a lattice, I perturb independently every point, then I take the Fourier transform, then this Fourier transform almost surely will be, from that you are able to recover the initial lattice, right? So it's very easy that this local perturbation cancel each other and you just keep the information of the dual lattice, yeah, the Fourier transform, yeah, or quasi that works also for quasi crystals and other like exotic structures. So there is And then there is a direction on curve histograms, right? So I have a curve, and then I don't do a discrete histogram, but I have a whole continuous distance histogram for that. And there are some, so here is a big survey paper on all of these type of problems of distance histograms. And the rest with areas, triangles, and other algebraic structures is not covered in this survey. In this survey plus new results, plus counterexamples. Yeah, and so what does it mean that these pathological examples are zero measure, right? So there was this paper in Physics Review Letters, right? That was saying, not maybe exactly in this paper, but the message was more or less, even if the data don't contain bad configurations, the learning still suffers if bad configurations are around, right? So you see the idea is that I have pathological configuration, you never see them because they are zero measure. So let's forget about it. Let's forget about Weisfeiler-Lehmann, right? But this work was they were finding some specific type of configuration which seem realistic for small molecules, for which already in these cases, kind of just looking at sets of distances was not a big strong information, right? So something like the distance histogram is not enough to distinguish them. And therefore, if I work only with collections of distances, it will be hard to learn, right? And then, the skeptic would say, yeah, but you never see those. The data set avoids them. So then you don't care, no? Shouldn't you not care? But the idea was that, well, if a molecule is going to shift from this position to that position, and I have to predict that, then the fact that the trajectory in the latent space of my model is going to cross itself is going to give constraints that are bad for my task. Yeah, but still the question is, can you do that does it happen in big realistic molecules, right? I don't know the answer to that question. But the question that I would say that it's interesting is, can it be formalized, right? So the proof of this distance histogram result, I take it as an indication of the general principle. The proof is that, well, they check when are this set of distances equivalent to these distances up to isometry, right? So you have to do some work with algebraic invariant. Kemper is famous for algebraic invariant theory, algorithmic invariant theory. And then they show that a superset, some superset of space of pathological configuration is a zero of some polynomials, right? Stays in some ideal of polynomials. So the zero so it forms a surface in this space, right? But what they don't have a good so there are results, but they are kind of might be unsatisfactory because it seems like the superset, this superset of the pathological configuration, actually becomes dense as the number of points goes to infinity. So, well, I have just some bad configurations, so let's forget about them. But careful, because if you increase n, the ones that you have a certificate that is a superset of your bad set is going to become dense. What is open is what happens actually on the bad set itself, not this superset that is easier to deal with, right? So in order to convince any mathematician that the data don't contain bad configuration, you would have to give a criterion. Even if the data don't contain bad configuration is bad, you have to have a good density bounds for the pathological set. So say the pathological set is sitting everywhere, and so no matter what your data is, it will always going to be close to it and ruin your learning, right? That's the result that is missing, right? So the last part, very fast, expressivity. We talk about it. Now another notion is universality. So can you, if you have expressivity, can you approximate any function that, say I have a class of neural networks that can separate objects in a given category, right? So graphs. Graphs can be separated by some version of WL, right? Then there is another question: can we actually approximate any function in that expressivity class with my architecture, right? So there is a result, but if for neural networks with only one hidden layer, if they are too simple, then there are negative results where the universality class is different from the expressivity class, right? So how complicated has to be your network so that you don't have expressivity distinct from a universality? That's one kind of formal question. And another question is the learnability class. So there is this observation in some recent papers by Petrache and Manolake, that is like your student, and then where they show that actually if you relax equivariance during training in an actual equivariant task, this is making the convergence easier, and actually you get better accuracy in the end for the equivariant task, right? So it means that something about the loss geometry is interfering with the gradient descent. Right, so that's an interesting open question. If you have a universality, do you have learnability? Right. So these are. This is all I wanted to say. Yeah.
Any questions? Perhaps a stupid question, but like
No.
the isometry part, when you do this reconstruction,
Yeah.
would it also be interesting to look at other notions of, like not symmetry, but let's say translation or scaling or other kind of groups that can act on,
Yeah.
on a space?
That's true. You could. That's interesting. You would. Besides the isometry group, there are many other might be other interesting groups. I mean, there is. I would like to know some example that are. So for sure, the question is tractable in some cases, but I don't know some realistic example on which to start sweating.
I mean, like the reconstruction that you do with the local information.
Yeah, that can be extended much beyond this synthetic geometry setup. Yeah, but so where to start? Yeah.
No, I mean, like instead of only looking at distances, you're looking at more relaxed things, right? Like if you only want to be like, you know, reconstruct up to scaling or something, you don't need precise distances. You need some other local information.
Yeah, you need something similar to the invariants that people have cooked up for your set of transformations. Yeah. And then I would like to, if I want to work on that, it would be interesting to know what is something with scaling. Yeah, one could try. Yeah, yeah, good idea. Yeah. Oops, sorry. Yeah.
So thank you very much for the talk. So in some previous slide, you talk about as n goes to infinity, the superset of the best set can get dense.
Yeah.
And you ask how to kind of understand like what the actual set is like, because we mostly care about the actual set. So
they manage just to control something for which they don't have a criterion that is actually equal to the set of the configuration.
Yes. Yeah. So do you know, or if there are approaches for us to be able to characterize, or I don't know, tighten
to restrict
the
it,
relation?
restrict it a little bit. No, I don't. I know. Yeah, that's the big question. Yeah. That's. It seems like I don't have enough for that. I don't know a toolbox that can help for it. It would have to do with representability of distances in some space. So basically, where you have to start with is to notice that there is some numerological coincidence between these values, and this will allow you at least to restrict a little bit more your set. Yeah, but this is very weak information that I have. So more than that, I don't have the expertise to say.
Thank you.
Again, a silly question probably. like when you had this kind of measure zero set at the end, right? So the bad points or the bad data.
Yeah.
Can you always avoid it by just introducing some noise?
Yeah, you can.
Okay.
But I mean the main claim there is that so you move the wave. So there is I mean at a certain point in the history of deep learning, some people were saying that the loss landscape of deep learning had a lot of saddle points and you get stuck in one of them, and then after a while people realized that no, you don't get stuck in all of them. So we are at the saddle point level in this story. So there is no simple way to convince that these points are you should forget about them, and there is no simple way to do this other thing, which is the thing that I propose to study the density of these points, right? So in a sense, it could be due to historical knowledge. It could be that is stochastic, the gradient descent. So even if in simple examples you see kind of difficulties to learn some shapes, maybe in general that was like not representative. You would need to do many experiments in order to do that. Yeah.
If I may make a comment on this, this question was of a great interest to people who were using these sort of methods for learning, say, force fields in chemistry, and even going back to before the neural networks era. And you can kind of understand why it's of so much concern, because neural networks are complicated, it's difficult to know exactly what the hypothesis space is, and so on and so on. But prior methods really had a very strong bias towards learning smooth functions. So there's this whole picture that you're learning a smooth energy landscape over possible configurations. Now, if there's like these lines of configurations which collapse onto the same representation, that means that your configuration space is kind of stitched together, and all of a sudden totally physically unrelated configurations are forced to assume the same energy. It can be a serious problem there.
Yeah. So, but I mean for me I'm not an expert on this history. But my understanding is that there is still the question whether this is close to the data set or not. This situation is close to the data set or not, or there is something like the stochastic gradient descent part of the story that kind of makes the critiques void, or the overparametrization. You know, overparametrization makes you go out of the plane and somewhere else, and I don't know. Probably I'm being naive here. I don't know.
Okay, then let's have a coffee break. See you again in 30 minutes.